Hey there, hello everyone, welcome to another video. In this video we're going to solve one of the problems of Goldstein's classical mechanics book, which is the first derivation of chapter 1. My name is Ricardo, I'm a professor at the Physics Institute of the Federal University of Goiás. In this derivation, we need to show that for a single particle with constant mass, the equation of motion implies the following differential equation for the kinetic energy. The time derivative of the kinetic energy is equal to the scalar product between the force and the velocity. And in the second part of this problem, we need to show that while if the mass varies with time, the corresponding equation is the time derivative of this product, mass and the kinetic energy, being equal to the scalar product between the force and the momentum. Okay, so let's solve the first part. We are in the scenario with constant mass, and the kinetic energy is defined as 1 over 2 mv squared. But since in this right-hand side of the equation, we do have a scalar product, let's write the kinetic energy as a scalar product as well. So this is 1 over 2m and the scalar product between v and v dot v. Calculating the time derivative of the kinetic energy of this function here, we do obtain 1 over 2m, which is a constant factor, and the derivative of this product, v dot v, which is the derivative of v multiplied by v plus v multiplied by the derivative of v, which is 2 times the time derivative of v dot v, since we are using the commutative property of the scalar product. So now these factors cancel out, and since the mass is constant, we may write it inside the derivative. So we obtain the derivative of mv dot v, and mv is the momentum, is the definition of the momentum. So now we have the time derivative of the momentum, which is the force, in a scalar product with the velocity, which is exactly what we were looking for to solve. But we can solve this problem in using a different method. We can use the equation of motion and try to verify if this product is going to be the time derivative of the kinetic energy. So, instead of writing the force, we are going to write it as the time derivative of the momentum, which is the force, of course. And since the momentum is mv, and m is a constant, so we can write it as m time derivative of v dot v. And since we used this in the previous slide, the derivative of this product is 2 times the derivative of the velocity dot the velocity. So now we have this term here, which is this right-hand side of this equation here, except for the 2. So this term is 1 over 2 the derivative of the product. So since we have the mass, this is going to be m over 2 and the derivative of v dot v. Since the m over 2 is a constant factor, we may write it inside the derivative, and the result is the time derivative of this quantity here, 1 over 2 mv squared. And this is called kinetic energy. So we just solve the equation. We just verify this equation using this second method. Now the second part of the problem. If the mass varies with time, the corresponding equation is this one. So this is the scenario. The mass varies with time. Again, the kinetic energy is 1 over 2 mv squared, which we can write it as 1 over 2 mv dot v. But since F, the force, is the time derivative of the momentum, and here this quantity is multiplied in a scalar product with the momentum, let's write the kinetic energy as a function of the momentum. So if you multiply this equation here by m in the numerator and in the denominator as well, this is going to be m squared v squared, which is p squared, over 2m. And doing the same, writing this as a scalar product, we have 1 over 2m p dot p. Okay, and we are going to calculate the time derivative of mass multiplied by this term here, the kinetic energy. So mass will cancel out with this mass here. We need to calculate the time derivative of 1 over 2 p dot p. And the result of this is the time derivative of p dot p, since the derivative of this product will result in a factor of 2, which will cancel out with this 2 here. And the result is this one. This term is exactly the force, so we just solve the problem. This is the force dot the momentum. So we just verified that we can write this equation as this time derivative of mass and the kinetic energy. But solving these in a different way, this product here, the force dot the momentum, is the time derivative of the momentum dot the momentum. And using this equivalent term as we did in the previous slide, we have that the time derivative of this product is 2 times this derivative of the momentum dot the momentum. So since we have this term here, which is the same as this one except for the 2, this is going to be 1 over 2 and the time derivative of this product. And we can write this 1 over 2 inside the derivative, and p dot p is the same as p squared, and multiplying by m in the numerator and in the denominator as well, we have this term here, and you can identify that this term is the kinetic energy, p squared over 2m, p squared over 2m. So we have, as a result, the time derivative of mass multiplying the kinetic energy as the left-hand side of this equation. Hello everyone, welcome to another video. In this video we're going to solve one more problem of classical mechanics by Goldstein, which is going to be Derivation 2 of Chapter 1. My name is Ricardo. I'm a professor at the Physics Institute of the Federal University of Goiás. So we need to prove that the magnitude r of the position vector for the center of mass from an arbitrary origin is given by the equation m squared r squared is equal to m, the summation over I of mi ri squared, subtracted by 1 over 2 double summation over I and j of mi mj r ij squared, this quantity that we are going to show what it is soon. So first, what is r? What is this vector r? The vector r defines a point known as the center of mass of a certain system of particles. So this is a definition. And if we write this value, this mass, on the other side of the equation, we will get m multiplying this vector r being equal to this summation here. And if we square this equation, we obtain m squared, r squared, which is exactly what we are trying to prove what it is, being equal to this summation multiplied by another summation. But we need to distinguish between the index of this summation and of this other summation. And we already discussed that in this introduction to the index or tensor notation. If we do not distinguish the indices, we will not have the crossed terms. For instance, R1 dot R2 and so on. So if you use only the same index, I and I, for instance, then you will not have the cross terms. So that's why we need to use that. This is a sequence of terms and this is another sequence, and we need to multiply each term of each sequence by each other. So as a result, we have a double summation over I and j of mi, mj, and then the scalar product between ri and rj. Okay, but what is this quantity rij? This vector is the difference between ri and rj for the particle I and the particle j. So this is the vector rij. And if we square this equation, we have the quantity that we are looking for here, rij squared, and it is going to be ri squared plus rj squared minus 2 times ri dot rj. And we want this scalar product. So I'm going to rewrite this equation as the product, the scalar product ri dot rj being equal to 1 over 2 of ri squared plus rj squared minus rij squared, which is this equation here. So now we need to use this equation inside this one and then try to prove this equation here. So m squared r squared is going to be 1 over 2 and the summation, the double summation over I and j of mi, mj multiplying ri squared, which is this first term here. The second one is similar to this one, but instead of ri squared is going to be rj squared. And the third one minus 1 over 2 double summation mi, mj, rij squared. Here we are writing that I is different from j just to emphasize that, because in case it is equal, then this term is going to be 0. Rij, by its definition, is going to be 0. There is no difference between the vector and itself. So now let's rearrange these terms here and try to find the solution. The first one is going to be 1 over 2, and then since here we have a double summation, one is over I and the other one is over j, and we have only this mass with the index j. So we can write it as the summation over j of mj multiplying the summation over I of mi ri squared. And we will do an equivalent thing in this other term here. We have only this term with the I index, so we have this summation over I of mi, and then the summation over j of mj rj squared. And we will just repeat this last term here. Okay, so we can solve the summation of mj over all possible values of j. This is exactly the total mass of the system, which is capital M. So the result of that is M, and we write it over 2, multiplying this term here. And we do the same here. The summation of mi over all possible values of I, it is the mass of the system, the total mass. So this will result in m over 2 and multiplying this term. And again, we just repeat this last term. Okay, so now we have a summation of this quantity. The mass of each particle multiplied by this quantity are I squared. And here we do have the same thing, but with a different index. But there is no issue on the index. It could be any letter. The quantity is the same, and it is being summed over all possible values of I or j. I mean, all possible particles, all particles on the system. So this quantity is the same of this quantity. And we then can write it. Since this is m over 2 and m over 2, this is going to be just m. M of this quantity, let's use the index I. We could use a different index. And the summation over I of mi are I squared. And again, we just repeat this term. And this is exactly what we were looking to prove. We just proved this equation. Hello everyone, welcome to another video. This is the solution of another problem of classical mechanics by Goldstein. I'm Professor Ricardo, and in this problem we are going to suppose that a system of two particles is known to obey the equations of motion 122 and 126, which are these two equations here. So we're going to suppose that this system of two particles is known to obey these two equations. And from the equations of motion of the individual particles, show that the internal forces between particles satisfy both the weak and the strong laws of action and reaction. So from the equations of motion of the individual particles, we are going to show that the internal forces satisfy both the weak and the strong laws of action and reaction. First, consider the position of the center of mass, R, and for the system of two particles, we have that the mass multiplied by the vector R is equal to the summation of mi Ri, which in our case is m1 R1 plus m2 R2. So the equations of motion of the individual particles are, for the particle 1, m1 multiplying the acceleration of particle 1, which is the second order time derivative of R1. This is equal to the external force over particle 1 plus the internal force of particle 2 over particle 1. We have an equivalent equation for particle 2. m2 multiplying the acceleration of particle 2 is equal to the summation of all the forces acting on particle 2, the external force and the internal force of particle 1 over particle 2. And we are going to sum these two equations. So, since the mass is a constant, we can write it inside the time derivative for both cases here. And the sum of time derivatives is equal to the derivative of a sum. So we can write the left-hand side of this equation as the time derivative, second order time derivative of m1 r1 plus m2 r2. And in the right hand side, we are going to write the external forces F1 and F2 plus the internal forces F12 and F21. Now, this quantity here inside the parentheses is equal to mr. So we are going to write the left-hand side of the equation as the time derivative of mr. And this quantity, the summation of the external forces over particle 1 and particle 2 is equal to the total external force, which is written here. Our system is known to obey this equation here, so this is a definition. The total external force is equal to the summation of the individual external forces. So the first term of the right-hand side is the total external force, and we are going to write these two internal forces here. And since the mass is a constant, we can write it outside the derivative, and we just obtained the left-hand side of this equation here. And we just repeat these three terms. But since our system must obey this equation, this pair of internal forces must be equal to 0. Why? Because mass multiplying the acceleration of the center of mass is equal to the total external force. And then this pair of internal forces added, this is equal to 0. Or we can say that F21 is the negative of F12. And this is the weak law of action and reaction. This is exactly the weak law of action and reaction. Okay, so what about the strong law of action and reaction? The equation of motion for particle 1 is the time derivative of the momentum being equal to the forces exerted on particle 1, the external force and the internal force. And if we multiply this equation by R1 in a cross product, so we have the R1 cross the time derivative of the momentum, R1 cross F1, external F1, plus the R1 cross F12. Okay, and we are going to use this identity. Consider this identity. The time derivative of this product, R and mv, which is the momentum. So R cross the momentum, mv. This is equal to the derivative of R, which is the velocity, cross mv, plus R cross the time derivative of the momentum, mv. But this first term is null. This is equal to 0 because we have a cross product between v and v, okay, multiplied by a constant, but this is a cross product between the same vector, so this is equal to 0. And then we have that this time derivative of this product is equal to this quantity here. And this quantity is exactly what we have here. R1 cross the time derivative of the momentum. This is the momentum. So we're going to write this left-hand side as the time derivative of R cross the momentum of particle 1. We are talking about particle 1 by now. And then we just repeat this right-hand side of the equation. But R1 cross P1 is the angular momentum for particle 1. So We can write this equation as the time derivative of the angular momentum, and R1 cross the external force over particle 1, this is the torque from the external force on particle 1. So we're going to repeat this last term and obtain this equation here. We can write the same equation for particle 2. Doing the same considerations, we can obtain this equation for particle 2. The time derivative of the angular momentum for particle 2 is the total is the torque, the external torque over particle 2 plus this product R2 cross F21. And we are going to add these two equations. So in the left-hand side of the equation, we have the time derivative of L1 plus L2. And here we get the external torque over particle 1 plus the external torque over particle 2, and these two terms, R1 cross F12 plus R2 cross F21. Okay, so this quantity inside the parentheses is the total angular momentum. So we get the time derivative of the angular momentum. And the summation of the external torque over the individual particles, 1 and 2, is the total external torque. And then we are going to consider the weak law of action and reaction that we just showed that this is true, that F12 plus F21 is equal to 0. Then F21 is the negative of F12, and then these two terms here, we can write them as R1 minus R2 in a cross product with F12, because we wrote this F21 as the negative of F12. Okay, but since this system is known to obey these two equations here, this quantity must be equal to 0, because we know that the time derivative of the angular momentum is equal to the external torque, the total external torque. Then this quantity must be equal to 0. And then, since with this equation here we concluded that the weak law, this is the weak law of action and reaction, the forces are equal and opposite. Now, this equation here is showing to us that the internal forces, in addition to being equal and opposite, also lie along the line joining the particles, because the product of the internal force with the line joining the particles, this is equal to 0. Then they are in the same direction. And this is the strong law of action and reaction. Thank you. Hello everyone, welcome to another video. In this video, we're going to find out if a differential equation of constraint is integrable or not. In other words, if a differential equation of constraint is holonomic or not. This is the solution of one more problem of classical mechanics by Goldstein, and I'm Professor Ricardo Gomes. So the equations of constraint for the rolling disk, equations 139, are special cases of general linear differential equations of constraint of the form summation of gi times the differential dxi is equal to 0. For the rolling disk, the differential equations of constraint, the equations 139, are these two equations here. A constraint condition of this type is holonomic only if an integrating function f of the coordinates x1, x2 up to xn can be found that turns it into an exact differential. We're going to explain this method in this video. Clearly, the function must be such that del fgi del xj is equal to this partial derivative of fgj with respect to xi for all I different to j. Show that no such integrating factor can be found for either of equations 139. So we're going to explain the method and then we're going to use it to show that there is no such integrating factor for either of these equations. In few words, if there is an integrating factor, then the differential equation of constraint is holonomic. So we're going to multiply the equation of constraint, which is 0, by the function f, which is the integrating function, integrating factor. And this is equal to this exact differential. If we integrate that, we would obtain a function g of the coordinates x1, x2 up to xn, and this arbitrary constant of the integration. And if we write this equation in this form, we will identify that as a holonomic constraint. This exact differential, we can write it as the partial derivative of g with respect to x1 times the differential dx1 and so on. And on the left-hand side of the equation, we can write this function multiplying the summation as the summation of the function f multiplying each term. And explicitly, this summation is going to be f g1 dx1 plus f g2 dx2 and so on. And we will identify this term multiplying the differential dx1, which is fg1, as the partial derivative of g with respect to x1. And we will do the same for the other terms. We know that since we are dealing with partial derivatives, the order of the derivative doesn't matter. So we can do the derivative, the partial derivative with respect to xi and then xj, or we can do the partial derivative with respect to xj, and then to xy. And this term in parentheses here, we just identify that as fgi. So that's why in a previous slide we wrote this condition, and this is part of the method to find out if there is or there is not an integrating factor. So for the first differential equation of constraint for the rolling disk, we are going to multiply that by f, and this function f is a function of the coordinates of the system, which is x, y, theta, and phi. And this is equal to the exact differential dj, which we can write it as del g del x dx plus the same for y, theta, and phi. And then we are going to identify what is del g del x. Del g del x is going to be the term multiplying the differential dx, which is f. Since there is no differential dy, del g del y is going to be 0. The same for del g del theta. And del g del phi is going to be the negative of a times f times the sine of theta. Now, we know that del g del x and then the partial derivative of that with respect to y is the same as this quantity here. So del g del x is equal to f, and del g del y is equal to 0. So we will obtain del f del y, this quantity is f, is equal to 0. And then we know now that f has no dependence on y. So f a priori was a function of x, y, theta, and phi. But now we know that it is a function of x, theta, and phi. And we are going to do the same procedure, but now with a different combination of partial derivatives. If we calculate that, del g del x, this is equal to f, so we will have del f del theta, and in this side, del g del theta, this is equal to 0, so del f del theta is equal to 0. And then there is no dependence on theta on this function f. F is a function of x and phi only. And if we do another combination of partial derivatives, del g del phi is equal to this quantity. And then we have the partial derivative of this quantity with respect to theta. And since del g del theta is equal to 0, this equation, the right-hand side of this equation, is equal to 0 as well. And now we know that a is a constant and f has no dependence on theta. And then it is a constant concerning since we are dealing with a partial derivative. And then if we omit this negative sign, because this is equal to 0, then the result is a times f times the partial derivative of sine of theta with respect to theta. And the result of that is cosine of theta. Okay, since this is equal to 0 for all values of theta, the function f must be equal to 0. And then there is no integrating factor for this equation of constraint. In other words, it is not holonomic. What about the other equation of constraint? So for the rolling disk, we have these two differential equations of constraint. We just solved the problem for the first one. For the second one, we will do the same method, the same procedure. We're going to multiply that by f, and this is equal to the exact differential dg. And this differential is del g del x dx and so on, the same as we did in the previous slide for the first equation of constraint. And now del g del x is the term multiplying dx, but since there is no dx on the left-hand side of the equation, del g del x is equal to 0. Del g del y is equal to f. Del g del theta is equal to 0. And del g del phi is equal to af cosine of theta. Following the same idea as we already did, del g del y is f, so we have del f del x on the left-hand side of this equation, and since del g del x is equal to 0, this is equal to 0 as well. And then f has no dependence on x. Another combination of partial derivatives, del g del y is f, so we have here del f del theta, and since del g del theta is equal to 0, this equation is equal to 0 as well, and then f has no dependence on theta. F is a function of y and phi only. And for this other combination of partial derivatives, del g del phi is equal to this term, so we have the partial derivative of this quantity with respect to theta, and since del g del theta is equal to 0, this equation is equal to 0 as well. Now, a is a constant. A is the radius of the disk. F, we just find out that has no dependence on theta, so For this partial derivative, it is a constant. And the result of that is going to be AF and the partial derivative of cosine of theta with respect to theta, which is negative of sine of theta. And we need that f must be equal to 0 for this equation be equal to 0 for any value of theta. And then we just got the same result for the second derivative, the second differential equation of constraint. There is no such integrating factor for either of the equations of constraint. The constraints are not holonomic. Thank you. Hello everyone, welcome to another video. I'm Professor Ricardo Gomes, and this is the solution of one more problem of classical mechanics by Goldstein concerning non-holonomic differential equations of constraint. So here we describe the system. The physical system consisted of two wheels of radius A mounted on the ends of a common axle, and we need to show that there are two non-holonomic equations of constraint, which are these two differential equations here, and one holonomic equation of constraint, which is this one. All the coordinates x, y, theta, phi, phi prime, and these constants c, which is a constant, a and b, they are described in the problem. It's not difficult to obtain these equations. What we are going to do is to show if they are holonomic or not. So let's start with this one. This is obviously an holonomic equation of constraint. Why? Because it is an equation of the coordinates only. You see theta, phi, phi prime, and constants. So there are no differentials, and then it is holonomic. What about these two differential equations? Let's start with this one. So we're going to multiply that by f, which is part of the method to find an integration function, if there is an integration function. We are not going to explain the method, we are going to use it, and this product is equal to an exact differential dg, and we can write it as partial derivatives with respect to the coordinates of g, which are the coordinates of the system as well, of x, y, theta, phi, and phi prime. So again, we will not explain the method, it was already explained in the previous video. We are going to use it. So del g del x is equal to f cosine of theta, and del g del y is f sine of theta, and del g del theta, del g del phi, and del g del phi prime, they are all equal to 0. If we calculate this quantity, we will obtain del g del x, which is f cosine of theta. Then we will need to calculate del phi of this quantity, f cosine of theta. And since del g del phi is equal to 0, then we have this equation here. And if we do the same, but instead of phi we use phi prime, we will have the partial derivative of the same quantity, but now with respect to phi prime. And now, what we conclude, since cosine of theta is a constant concerning the partial derivative with respect to phi or phi prime, then we will obtain here that del f del phi is equal to 0, and del f del phi prime is equal to 0. And then f, which was a priori a function of all these coordinates, now we just found that it is not a function of phi or phi prime. It is a function of x, y, and theta only. Now, if we do the same procedure, but now a combination of these partial derivatives, then del g del x is f cosine of theta, so we need to calculate del theta of this quantity, and del g del theta is equal to 0. And then, since this is a product, f is a function of theta as well. the same as cosine of theta, obviously. Then we need to calculate the derivation of this product, which is going to be del f del theta multiplied by the cosine of theta plus f multiplied by the derivative of cosine of theta with respect to theta, which is the negative of sine of theta. And this is equal to 0. We're going to do exactly the same, but instead of x, it's going to be y. So del g del y is f sine of theta. This is going to be the difference between this case and this one. And calculating this partial derivative of the product, we will obtain del f del theta multiplied by the sine of theta plus f multiplied by the cosine of theta, which is the partial derivative of sine of theta with respect to theta. And this is equal to 0. Okay, so we have these two equations, both containing this factor, del f del theta, and we're going to solve for this quantity. So del f del theta is going to be equal to the sine of theta over cosine of theta multiplied by f. And for the second equation here, del f del theta is equal to the negative of cosine of theta over sine of theta multiplied by f. So this is equal to this quantity here. So the sine of theta cosine of theta multiplied by f must be equal to this quantity here. And this factor and this factor, they are different to each other. And then we can conclude that f is going to be equal to 0. Must be equal to 0. If you prefer, you can work on these terms here and write this factor, 1 over cosine of theta sine of theta, multiplied by f, and this is equal to 0. And then, for all values of theta, we need that f must be equal to 0. Okay, so for the first one, we already obtained that the integrating factor is null, is 0. For the second one, we are going to write this term on the left-hand side, and then this quantity is equal to 0. We will multiply that by f, which is a function of all the same coordinates, and this quantity is equal to these terms here. Del g del x is going to be f sine of theta. Del g del y is going to be the negative of f multiplied by cosine of theta. Del g del theta is equal to 0 since there is no differential d theta on the left-hand side of this equation. And del g del phi and del g del phi prime, they are equal to the negative of 1 over 2 a multiplied by f. And then if you calculate these partial derivatives here, del g del phi is equal to the negative of 1 over 2a, which are constants, and then we will have del theta of f, of this quantity f. And since del g del theta is equal to 0, then this is equal to 0. And we conclude that del f del theta is equal to 0 and f is not a function of theta. This is going to be a very useful information for this equation. If we do the partial derivatives with respect to x and theta, del g del x is f sine of theta, so we need to calculate del theta of this quantity, and del g del theta is 0, then this is equal to 0. Okay, so f, we just find out that this function is not a function of theta. And then we need to, if we do not know that f is not a function of theta, we are going to calculate the derivation of this product, which is going to be del f del theta multiplied by the sine of theta plus f multiplied by the cosine of theta, which is the derivative of sine of theta with respect to theta. But del f del theta is 0. And then we have that f must be equal to 0 as well. The same for the first of the differential equation. So we have this result for both equations. And then no such integrating factor can be found for either of the equations of constraint. And we conclude that they are non-holonomic equation of constraint.